All right, good morning, everyone. Welcome to class. Where is my Zoom here?
Good morning.
How's everybody doing?
I am very good.
Awesome. All right. Okay, so plan for today. Okay, yeah, almost Friday. It's downhill from here in a good way. Once Wednesday is done, then it's like, oh, one more day of teaching, and then it's Friday. I don't teach on Fridays, but I have lots of meetings, which its own thing. Teaching is fun but tiring. Meetings are boring but easier. So here you go. So you guys have been working on chapter 2. They're interesting problems. Okay, so if you kind of working through the homework or the
Professor Globe.
Yeah, go ahead.
I forgot to ask about on the homework. I think you have one of them switched around. You have the combinatronics due this weekend and the partition due next weekend, because I got confused and I started doing combinatronics, but I was like, wait, we haven't done this yet.
Yeah, so I'm actually going to go over that today, but I did change the due date for that one. So I put the combinations homework due on the 18th because I realized that probably a lot of you haven't looked through the material yet, but I'm going to do a few examples from that section today. But thank you for bringing it up. I am changing the due date for that section, for the combination sections, to next week, next Saturday. Okay. All right. Cool. So yeah, today we'll go over section 2.3, partitions of sets, and I'll also go a bit through some combination stuff. Maybe just a little bit. I'm not sure if it will be better to just have some time for you guys to ask homework questions on the permutation homework. I want to encourage you to come to office hours in the evenings. It's fun. I had a couple of people in there last night, and my oldest, who's a math major, they're transferring to UCSB, going there in about a week. So we're working through some of these homework problems together. So if you're kind of working through them and they're like getting stuck or they're confusing, they're fun problems, but they're not. I can't look at them and right away tell you this is how they're done. I have to play around with. It's like, oh, okay, makes sense. It is this way and that way. Let's try it. Okay, got the wrong answer. Why is it double? Okay, that's why you need to divide by 2. So it's a process, and the more you do, and the more you kind of look at kind of methods for solving them, you kind of become more comfortable with them. But a lot of these are definitely, you can use multiple approaches. So you might say, somebody would say I did it this way, and somebody would say I did it this way. They're all kind of valid, but there's different approaches for doing them. But I encourage you to come to office hours. In Wednesday, Thursday, Friday in the evening, I have evening office hours. Okay, 8:30 to 9:30, but I'll stay open till 10 if there's demand. Okay. All right. So yeah, I'm gonna go over section 2.3, which is partition of sets. If time permits, I'll do a few examples from the combinations section, but you don't have to worry about that until next week. Okay, so you can do the combination stuff next week. So yeah, I changed the due dates on the combinations homework for next week. I probably should have had the partitions due this week, but I'm not gonna change the due date for that. I don't want to spring it on you. It's like, oh, hey, you have an extra thing to do. So this will be due next week too. But you do need this information completing problem set 2. So even if you're not doing the homework for it, I encourage you to do it. But even if you're not doing it, it is on problem set 2. All right, so partitions. Basically, we kind of touched on this a little bit in the first problem set. It's basically dividing up a set into smaller sets under some conditions. So the 2 conditions to have a partition for a set is that the subdivisions, they all get together and they contain all the elements in the original set. Okay, so you basically don't want to be missing any elements. So kind of, if you just want a visual, right? If I have the universal set contains, I don't know, this is your yard, right? And you want to divide it up into different sections. You're going to divide it up into different sections. So all of these are subsets of your yard. You might have them for different purposes. So if you take the union, if you put them together, nothing should be missing. So it needs to cover the whole area. And the second condition says if I is not equal to j, then AI intersect AJ is the null set. That means there's no overlap between the sets. So none of the sets will share anything with each other. So it's kind of a clean division. There's no overlap, but they need to cover all the elements in the original set in the universe. All right, so let's look at that. And that's related to the law of addition and law of inclusion exclusion, but we'll kind of look at that a little bit later in a few minutes. All right, so let's look at some partition examples. All right, so example 1, suppose your S is 1, 2, 3, 4, 5, 6. So that's your universe. Determine if these sets form a partition. So I basically have set 1 is 1, 2, 3, set 2 is 4, 5, and set 3 is 6. So if you put all the elements of these sets together, that means the union, we want all the elements of the original set to be accounted for. So if you list them, you get 1, 2, 3 from the first set, 4, 5 from the second, and 6 from the third. And you go, yes, this is equal to the original set. Okay, so that first condition is fulfilled. So condition 1 is done. Check. All right, second condition, we want to check to see there's no common elements between any of the sets. So you take the intersection of each of the sets with each other. And you can see visually that there's nothing common between 1 and 2. There's nothing common between 1 and 3. And there's nothing common between 2 and 3. All right, so A1 intersect A2 is the null set. Morning. A2 intersect with A3 is the null set. And A1 intersect A3 is the null set. Okay, so the second condition is fulfilled. So this, you say this forms a partition of the original set, yes. Yes. All right, so this is useful because if you have a partition, you know, then you know these two things. It's useful in stuff that you do with sets, with math, and we're gonna kind of keep coming back to this concept. It's like you kind of go, oh yes, it's a partition, therefore this could happen because you know the sets are not overlapping. So it's useful in stuff that we're gonna do later. All right, questions with that one?
Do you have a quick example of like real life of how that would be useful? Sorry, it helps me understand it a little better.
Okay, besides the one with the garden, let's see. I don't know, can you come up with something? So basically, you have to divide things up and things are not shared. So let's say I have 3 kids, right? 3 kids, and they want, I have candy. All right, that's a good example. So the universe is all the candy in my bag. All right, so the universe is all the candy. All right, and basically I want to divide it up. I want to divide the candy to the first kid, the second kid, the third kid are gonna get a certain amount of candy. I want all of it to be divided up, but they're not going to share, right? So it's not gonna be any common elements between the candy from the first kid and the second kid, because they're gonna fight if they're both eating the same piece of candy. So you're gonna wanna keep it separate. So basically it's something that is sort of, you want to share it out into different groups, not necessarily equally, all right? But all the things need to be accounted for, and there's no sharing. Okay, so sharing is caring doesn't work in real practice. Giving everybody the same thing works a lot better. All right. Okay. So yeah, when you work through the problem sets and problems in the problem set, there's a few partition of problems there. So hopefully that will kind of become a bit, you'll see it in different scenarios and become a bit more clear what you need to do with it. All right, so let's look at, is this a partition one or? Okay, all right, so now this comes to the law of addition, okay? So this theorem right here, the basic law of addition, I told you last time that there's like two basic rules for this combinatorics. One is multiplication, when you have the separate events and you have to multiply. Okay, you have 10 choices and 9 choices, 8 choices, or you multiply them together. The other big law is the law of addition, that if there are several ways of kind of getting to the same result that you want, then you add up all the choices. So this is kind of where partitions come in play when it has to do with sets. So if A is a finite set and A1, A2, AN is a partition of A, so that means they contain all the elements in the original set and there's no intersections, there's no commonalities. You also say the sets are disjoint, right? Then to find the magnitude of the set, you just add up the magnitudes of the smaller sets, okay? So in this example one, for example, the magnitude of S is, or the cardinality of S is 6, because it has 6 elements. The cardinality of A1 is 3, the cardinality of A2 is 2, and the cardinality of A3 equals 1. Then these have to add up to this. So 3 elements, 2 elements, 1 element makes 6 elements. So if it's a partition, so if you account for all the elements and there's no overlaps, then you have to have them adding up to the, how many elements are in the original set. Does that make sense? Okay, cool. All right, now the theorem, next theorem, law of inclusion, exclusion. You're gonna see this a lot in the last section in this chapter. If it's not a partition, okay, so if there is overlap between the sets, so you kind of, well, yeah, if A1, A2, AN if their union makes up the original set, so you account for all the elements, all right? But it's not a partition, they're not disjoint. Okay, so could be overlap between subsets. Then the union of the sets, it's not just the cardinality of the union, it's not just adding the cardinalities of the individual ones, you have to subtract the overlap, okay? So let me give you an example of that. All right, so basically you can't double dip, you can double count, okay? So let's say I have an example right here. Ignore this. We have A equals 1, 2, 3, 4, 5, 6. And I split this into 2. A1 is 1, 2, 3, 4. And A2 equals 4, Let's do 3, 4, 5, 6. Okay, so it accounts for all the elements, but there's overlap, right? They're not disjoint. We have common elements are 3 and 4. Okay, so the cardinality of A1 union A2. So A1 union A2 is the original set. So this is set A. So this is not going to be A1 plus A2. Okay, it's too many, right? So there's 4 in A1 and there's 4 in A2, and that would add up to 8, right? But there's only 6 elements in the union. So if you just add them up, you're double counting the 3 and the 4. You're double counting the overlap. So you have to subtract how many are in the intersection. So you have to subtract the 2 common ones so you don't double count them. Okay? Make sense? So you'll see that, so the intersection might be given and you have to figure out the cardinality of the big set, or you might be given the cardinality of the big set and the individual sets and you have to find the intersection. So you're usually given enough information to figure things out, but this formula would be useful if you don't know like one thing or another. So any of these could like be unknowns, okay? All right, so that actually makes it equal right here. All right, okay. So this is for 2 sets. So this is the inclusion exclusion law for 2 sets. This extends to more sets, okay? So you can kind of see the pattern here. So if you are taking, if you're splitting your original sets into 3 and there's overlap between them, they're not disjoint. So the cardinality of A1 union A2 union A3, you add up each of the cardinalities, but then you have to subtract the overlaps. So this part right here, let me see if I can blow this up a little bit. No, it's tiny. All right. All right. That's clear. All right, so you can basically, so you add up how many are each of the 3 sets, but there's going to be overlap, all right? So you have to subtract the common elements between each pair of sets. So you see this minus here in front of parentheses. You're subtracting the overlap between the first and second set. And you're also subtracting the overlap between the first and third, and you're subtracting the overlap between the second and the third. But what happens is that you're subtracting too much. You're subtracting the overlap between all the 3 sets when you do that. So you have to add back in the overlap of all the 3 sets together because you remove too many elements now, okay? So that's how it works with 3 sets. The one with the 3? Okay, let's look at that. So you can always make up your examples. So yeah, let's go here and let's do, and a Venn diagram might come in handy for this too. So let's see, I have A is, let's keep the numbers small, 1, 2, 3, 4, 5, 6 again. A1 is 1, 2, 3. A2 is 2, 3, 5. A3 is 3, 4, 6. Do I have all of them? 1, 2, 3, 4, 5, 6. Okay, good. So I have all the elements accounted for. All right, so let's see. A1 intersect A2 is 2 and 3. So that's the intersection between these. A1 and A3 is 3. And A2 and A3 is 3, right? Okay, so the cardinality of the union, so if I put all of them together, this is 6 elements, okay? The cardinalities of each of one. And I didn't have to have them all be 3 elements. It just kind of turned out that way. So this is 3 and 3 and 3. All right, so far I have 9, too many, okay? So now I have to subtract the cardinalities of the pairings, what's common between all the pairings. So this is gonna be 2 elements, A1 intersect A2, this is 2 elements. A1 intersect A3, that's 1 element, and A2 intersect A3, that's 1 element, okay? So you can see that all together, the intersections, there's 4, right? So now I have like 9 minus 4, which gives me 5, okay? So I took 1 too many. So you can see that the intersection of all these all together is 3, okay? So if I intersect A1, A2, A3, that they all have a common element of 3. So when you kind of subtracted the overlap between these, you subtracted this element 1 too many times. So you have to add it back in. So you have to add back in this common element. So you have to do +1, okay? So that gets you to what we need. Okay, so it's kind of a plus minus thing. So this extends to 4 sets, 5 sets, and so on. You basically have to, you add 1 at a time, you subtract the intersection over 2 at a time, you add back in the intersection of 3 at a time, you subtract the intersection of 4 at a time. So it's like plus minus to kind of account for either counting things too many times or subtracting them too many times. All right, any questions with this one? Okay. All right, okay, so let's do a couple of examples using these principle of inclusion exclusion. So these might be a bit familiar because we kind of looked at a couple of these problems in problem set 1 without actually me telling you about this. So this is kind of more formalized. So in a discrete math class, every student is a major in computer science or math or both. Okay, so we have 2 sets. So we have computer science, and I'll make a picture. And we have math, or we have both. There's overlap, okay? The number of students having computer science as a major, possibly along with mathematics, is 25. Okay, so the magnitude or the cardinality of the computer science group is 25. That means like in this whole circle, including the overlap, you're gonna have 25 students. The number of students having mathematics as major, possibly along with computer science, so the magnitude of the math people is 13. So in this circle right here, it's 13, the whole circle, right? All right, so let's make this pink. And the number of students majoring in both computer science and math is 8, okay? So this intersection is 8, all right. So let me actually write it 8 right here. All right, so this is C intersect M is 8, okay? Now in the Venn diagram, because there's 8 in common, you actually want to change this number to add up to 25. So you're going to have 17 plus 8 in the circle is 25. And you want to change the 13. 5 plus 8 is 13. So you want to have a total of 13 and a total of 25. Okay, so that's how you make the Venn diagram. So you can do the Venn diagram for visualization. It's not necessary because we have the formula. How many students are in the class? So assuming, because it says every student is computer science or math majors, there's no others, like strange liberal arts people who are just taking discrete math for fun. Anyway, bad joke. All right, so we have C union M is gonna be magnitude of C plus magnitude of M minus the magnitude of the overlap. So 25 plus 13 minus 8. We get, was it 4? 38 minus 8, which is 30. Okay. And you can see that from the Venn diagram too, right? If I add all the numbers, 25 plus 5 is going to give me 30. Okay. So that's how that principle of inclusion exclusion is useful in solving these kinds of problems. All right, questions there? All right. Okay, let's look at another one. Oh, this is a good one. Kind of going back with, there's a lot of number problems in the homework and in this course, like bit strings and rolling dice and flipping coins and just numbers, okay? All right, how many positive integers not exceeding 1,000 are divisible by 7? What do you think? How would I find that? All right. Any ideas? Just list them all and count how many? All right, so you could divide, right? You could do 1,000 divided by 7. All right, what do I get there?
Is this the one where we use the floor function?
Yeah, that one's useful, right? So, because if I divide 1,000 divided by 7, we get 142.86. But we have to round it, right? Because you can't have 142.86 numbers in the list divided by that are divisible by 7. So how many are there really? How do I round? This is gonna go to 142, right? Because there aren't enough. Yeah, you have to round down. So in math, there is a symbol that tells you to round down, and that's called the floor function. So the floor function has this sort of these half brackets, right? Like this. And this basically means round down. Okay, so this is called the floor function. And it tells you to round down. All right. There's also the ceiling function. We're gonna come across these occasionally, so it's good to kind of be aware of it. The ceiling function with the brackets at the top, you round up. Okay, in this case, you want to round down because you're not quite at having 143 because you have to go to 1,001 or 1,000. Do you need to go to 1,001 divided by 7? Yeah, you need to go to 1,001 to have 143 integers that are divisible by 7. Okay. All right. So, okay, how about 11? So if I do 1,000 divided by 11, what's that? And do the floor. So that's 90.9. I know that I need to round down, right? So if I do 1,000 divided by 7, I get 142.86. What I'm looking for here is how many positive integers are divisible by 7. So it doesn't make sense to have a decimal because I'm counting how many integers there are. Sorry? No, if you round it up, so the next number that's divisible by 7 is 1,001. That's divisible by 7 exactly. So in the first 1,000, if I had 1,001 integers, then 143 of them will be divisible by 7. So I'm missing the last one. So just 142 of them are divisible by 7. So that's why you need to round down. So it doesn't matter, like if you're 142.999, it doesn't matter. You don't have the last digits on the list. You only have 142 of them on the list that are divisible by 7. Okay, so this is kind of a natural use of the floor function. All right, so this rounds down to 90. So 90 of them are divisible by 11. So these are divisible by 7. These are divisible by 11. All right, okay. Is that it? Do I just add them up? 142 plus 90? This is 252? No, 200, 232? No, why not? What am I missing? The overlap, exactly, because a bunch of these are going to be divisible by both 7 and 11, right? So let's fit it in here somewhere. So we need to figure out the overlap. So we need to figure out all those numbers divisible by 77. All right. So 1,000 divided by 77, 12.98. All right. So this is going to round down to 12. Okay, so you got to subtract the overlap because you don't want to count those twice. So there's 220 of them. Yeah, so yeah, basically, because they're both prime, they don't have anything in common. 77 is the common denominator, common multiple of them. If it was something like 4 and 12, then the common would be 12. Or if it was something like 15 and I don't know, two numbers that don't have anything common, you find the lowest common multiple of them. But in this case, you just multiply because they don't have any factors in common. All right, questions on this? Okay, let's see if there's another good one. Okay, cool. Let's look at 4. All right, so this is a 3-set thing. Cool. Suppose there are 1807 freshmen at your school. Of these, 453 are taking a course in computer science. So computer science is 453. 567 are taking a course in math. And 299 are taking courses in both computer science and math. Let's make a muck this time. Okay. So let's look at how many are not taking a course either in computer science or in math. All right. Okay, so let's figure out the union of these. Okay, so this is the intersection, right? So the union is gonna be C plus M minus the overlap. All right, so 453 plus 567 minus 299. All right, so 453 plus 567 minus 299. This gives me 721. Okay, so this is how many are taking either math or computer science or both. All right, okay, so either math or computer science. Right, so now I have to figure out how many are not taking a course in either computer science and math. So we look at, that's how many freshmen are in total. So subtract the ones that are taking either math or computer science. And we get that 1,086 are outside this group, okay? So if you want to visualize it with a Venn, So we have this big rectangle here, which are all freshmen. Right. Inside this, we have a circle for the computer science and a circle for the math. Okay, so there are like 299 in the middle. That's the overlap. Computer science in total is 453. So 453 minus 299. So there's 154 computer science. There are not also math majors, but together, if you add these numbers, you get the 453. And 567 minus 299, we get 268. All right, so all people math together should add up to 567, but 268 are math majors who are not computer science majors. So the union of these circles, if you add them up, this gives you 721 in here. So outside the blue circles is all those other people who are losing out and are not computer science or math majors. Okay, so that's 1,086. All right. Okay, any questions on that one? Okay, so this was not a 3-circle one. I was just still 2 circles. All right, cool. Okay, let's do the next example. All right, Spanish, French, and Russian. All right, so we have, how many took Spanish is 1, 2, 3, 2. How many took French is 8, 7, 9. How many took Russian is 1, 1, 4. Okay, 103 is both Spanish and French. So intersection of Spanish and French is 103. Spanish and Russian is 23. And French and Russian is 14. If 2,092 students have taken at least one Spanish, French, and Russian, how many students have taken all 3 languages? So we're given the union suffer is 2092, and we need to find the intersection of all 3. Okay, so that's what this problem is asking us. So you can see how this law of inclusion exclusion really kind of simplifies things for these kinds of problems. Venn diagrams are fine, but even those are kind of a pain to write. But if you know the formula, just like you kind of just collect all, kind of assign numbers to each of the things in the formula and plug it in, right? So we have suffer is S plus F plus R minus the overlap between each of the pairs. So I'm going to do minus the whole parentheses there. And then plus the overlap of the 3. All right, so plug in the numbers. So we have, let me use a different color because it's getting a bit boring. 2092 equals 1232 plus 879 plus 114 minus parentheses, all the overlaps added together, and then plus the question mark. All right, so plus the thing that we're looking for. You can call it X or whatever, okay? So do the math. So we have 1232 plus 879 plus 114 minus the things in parentheses, 103 and 23 and 14. So this gives me 2085 here. So subtract 2092 minus 2085. And I got 7. All right, so 7 of them are taking all 3 languages. Wow, I'm impressed. All right, any questions with that one? Okay. All right, I'm gonna get you guys in breakout rooms to work on problem set. I probably won't have time to go over combination stuff today, but we'll do that next week. You are welcome to start watching the videos ahead of time. I know some of you already have. All right, so. All right, let me share for those problems. You guys can tell me which ones you're working on.
And we got 3 lines on it. I'm having a problem understanding exactly what it's asking for.
Okay, here's that. That's 10.
It's just like, is it asking that? I think I you understand, but is it asking for like, when it says no repetition, what is that?
It means that 1 only appears once, 2 only appears once.
Oh.
So,
Right.
so you're using digits 1, 2, 3. And you couldn't have something like 1, 1, 2, right? Because you're repeating 1, okay? So in part A is just asking you to, right, it's asking you to list them. So 1, 2, 3 is a choice. 1, 3, 2 is a choice. So yeah, just list all the possibilities. Funny. They whether figuring out whether the problem is easy or not.
Yeah,
right. So it's kind of like, what is it even asking me? So you have to get this is a big part of what you're learning in this class, how to read math and figure out what it's asking you. And then it's like, oh yeah, this is actually easy, but some of them are difficult. So, right.
I'm like waiting for like the trick question.
Yeah, right, exactly. Yeah, so read 311 and see if you can figure out what it is, and I'll assist if you get stuck. All right, let's go to breakout rooms. Do I go here? No.
Professor, you're muted if you're talking right now.
All right, thank you. Welcome back, everyone. Any questions on any of these problems before time runs out? 13? Oh, that's the shrubs.
I don't understand that.
All right. So let's look at 13. So this is the circular permutation thing. All right, so A, how many ways can a gardener plant 5 different species of shrub in a circle? So we have azaleas, bougainvilleas, camellias, daffodils, and A, B, C, D, E. Evergreen bushes? I don't know. So this is a question. So this is like the circular permutation. So in a line, it will be 5, 4, 3, 2, 1, but which is 5 factorial. Oh, sorry. But in a circle, because the rotations, there are 5 rotations, and they're going to be identical because they're next to the same types of flowers. You divide by 5, so you get 4 factorial. Any questions with that one? Yeah, you got to put them. If you put them in a circle, then the rotations are identical. All right, what's the answer if 2 of the shrubs are the same? Okay, so if 2 of the shrubs are the same, then you have the 5 factorial, but you divide by, so you still get 4 factorial, but now because 2 of them are identical, then you have to divide by 2 factorial, which is 2, because those instances are the same. Okay, so whenever like things are identical within your permutation, so if you have 2 identical things, you divide by 2 factorial. If you have 3 identical things, you divide by 3 factorial, and so on, to get rid of the repeats. All right, any questions with that one? Does that make sense? All right.
Professor?
Yeah.
So if there's like 5 the same ways, we don't have to do the factorial, but if it's like an identical item within the set, we have to divide by factorial. Am I getting this right?
Say the first part again.
Like in letter A, so there's like 5 ways that they are the same.
Yeah. So yeah, if it's 5 different things, they're not repeating, so it's going to be the factorial. We divided by 5 because it's in a circle, so that's why we got 4 factorial. But now when you're saying it's going to be repeated, then the order like of these 2 things are interchangeable. So you divide by 2 factorial because 2 of those things are identical. Okay.
Yeah, my question is, how do we know when to use the factorial sign?
So you know to use the factorial because you're looking at how many ways the things are arranged. Yeah, I'm trying to explain. So here, like we divided by 5 and not 5 factorial because there were 5 rotations around that circle. Okay, so that was not factorial. This is 2 factorial because let's say I have one A, B, C, D, E. So I have A, B, C, D, E. All right. Let's say 2 of them are identical. So I have these are both A's. Okay. So we divide by 2 factorial because this is basically how many ways do I arrange these 2 bushes amongst each other, right? So it's going to be AA, or if I switch them around, it's going to be AA, right? So it's kind of, if it was AB and BA, right? So there's 2 factorial because you have 2 things that you're trying to see how many arrangements of these 2 things, right? So if they become identical, then they're the same thing. So you don't want to count them twice. If 3 of them were identical, if you had ABC, then you're going, what if I make them all the same? Right? You have to count how many of them are going to be repeats. So you're going, oh, this is going to be 3 factorial. This is going to be like 6 different arrangements that you can make out of ABC, which are no longer different. So you have to divide by 3 factorial. So this is kind of ACB and BAC and BCA and CAB and CBA. So there's like 6 different arrangements that you can make out of 3 of them. But if they become identical, 6 becomes 1. So you have to divide by 6 in order to get rid of all the repeats. Does that make sense?
Yeah.
Good. All right, and then finally, what is the answer if all the shrubs are identical? Well, if all of them are identical, then it's just like, there's only one way of arranging them, right? So that would be 1. All right, 15. I know time's up, but this is, you're welcome to leave. But I'm sticking around for office hours. So if you want to ask more questions, that's fine. So let's look at 15 now. All right, that's a good one. So this gets into partitions, but this is an interesting problem because it's geometrical partition. So instead of just having like list of numbers in a set, then you kind of look at sets that have some sort of picture to them, some sort of geometry. So let's look at part A. So our universe is R squared. This is 2-dimensional space. Okay, which means like the members of that set are coordinate points. So X, Y, and you're thinking that you're drawing them on an XY axis in 2 dimensions. So that's kind of the beginning part here says, these are a typical member of these sets that I'm gonna have in my partition. So a typical member is a coordinate point where X and Y are real numbers, okay? Now this second part gives you some sort of formula or rule of how these are related to each other. So it says that X plus Y equals C. I know from algebra that this is the graph of a what? Not a circle. It's just a line with slope. Yeah, it's a linear thing. Good. So now C could be any number. So basically for each value of C, you're gonna get a different set. So if C is 0, this is your set A0. So you have X plus Y equals 0. All right, so you go, oh, this is this line going through the origin. For C1 or C0.2, I could have another set, set 0.2, X plus Y equals 0.2. Slope stays the same, y-intercept changes, so you have another line here. Okay, let's say I have C equals 1, X plus Y equals 1. Still a line, still slope -1, but the y-intercept is at 1, okay? So you can see that each of the sets in my division, in my partition, we're trying to see if it's a partition, but each of the sets are going to be aligned with slope -1, okay? So now the question says, is this a partition? So we have to see the 2 conditions. If I put all these lines together, is the union going to be the entire 2-dimensional space? What do you think? Yeah, it fit because C is a real number. I can fill all the gaps and make a solid 2-dimensional space. Check. The second is the intersection between 2 sets has to be null. Do any of the lines intersect? No, because they have the same slope. So you go, yeah, this is a partition. Right, so I partitioned my space by slicing it into lines, okay? All right, let's look at part B. Part B is circles. And it's a general circle. It doesn't have anything specific. So each set is a circle. So I have a circle. I have another circle. Yeah, so this is no Y. What condition does it miss? They are totally intersecting with each other. So yeah, the intersection rule is broken, right? Because there are common points that belong to both of them. All right, in part C, we have circles centered at the origin, all right, including the origin. So origin is one of the sets, and then you can x squared plus y squared equals r squared. You can choose r to be any real number. So you can have radius, different radii are real numbers like this. Do these form a partition? Do they fill up the entire space? Right, just like the lines, right? Do they overlap? No, because they are centered at the origin, right? So they're not going to overlap. So this is a yes.
Why can't B fill that same criteria?
Why can't B?
Fill that same criteria. It just says a set of all circles.
Because it doesn't say that they're centered at the same place. But you have to assume the most general thing.
Oh, okay.
Right? So if it doesn't give you a certain condition, you have to assume that it could be any circle in general. Right? Okay, D. So D says they're just coordinate points. So each set in my partition is one point in space. So basically each set has a singular member. All right. So like set A is gonna have like coordinate point 1, 2 in it. And set 2 is gonna have coordinate point 1.9 and 100.7. So each set has one singular coordinate point in it, okay? That's what that says. All right, so if I have a point here, 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 can I fill R2 by drawing an infinite number of coordinate points? Yeah, so it fulfills the union thing. Do they overlap with each other? Yeah, so one detail about partitions is that if two sets are identical, then these are not considered as overlapping. They're just considered that they're the same set. They're only considered to be overlapping if they're not exactly equal to each other and they share members, right? So because these are single members, they're not gonna have anything in common with each other because they either have the same exact elements, which make them not overlapping, or they have different elements, which make them non-overlapping. Okay, so the intersection is also fulfilled. So yeah, that's a partition too. Yes. Okay. All right, let's look at my chat. Okay, any other questions from anybody who's still hanging around? That is a fun one. I like that one a lot. It kind of gives you a better idea of what a partition is, just a different perspective on it.
Professor?
Yeah.
Do you have other office hours other than Tuesday and Thursday?
Wednesday, Thursday, Friday in the evening from 8:30 to 9:30.
Okay, thank you.
You're welcome.
Go over for the homeworks.
Sorry?
Can we also go over for the homeworks?
Oh yeah. Last night there were a couple of people. That's what we did. We just worked through several problems from the permutation homework.
Oh, okay. Yeah,
Oh,
because
yeah.
I have trouble in the permutation problems as well.
Yeah, if you want to come in and just spend an hour and an hour and a half working on homework with and check with me and other students in there, that's a perfect thing to do.
Okay, thank you. So it's from 8:30 to 9?
8:30 to 9:30, and if people are still there and wanting, I'm happy to stay till 10.
And this is on Monday, Wednesday.
No, Wednesday, Thursday, Friday.
Or Wednesday, Thursday.
Yeah, so tonight is open, tomorrow night is open. Yeah, I find that Monday, Tuesday, not many people come because most things are due. Yeah, most things are due at the end of the week. So if I've had office hours like 5 days a week, and mostly Monday, Tuesday, I'm just there grading. But towards the end of the week, it gets busier. Lauren, you had questions from homework? All right.
I just want to know if I did 11 right for A.
Yes, that's correct.
Okay.
Okay. Because yeah, you have n choices for each spot.
Yeah.
Okay.
So for 11B, I'm not sure that I.
So it says that it's not repeated. So you basically have 3 spaces because it's a triplet. And you have n choices for the first one, but then you can't repeat. So how many choices are you going to have for the second one?
How did you do that? Can you help me read like from this to what you just said?
Okay, yeah, let me put that up.
There's a set of ABC in which ABC exists in the universe A, each coordinate is different.
Yeah.
Is that right?
Yeah, so when you're doing, okay. So yes, so part B is saying that you're gonna form a triplet, ABC. Okay, so it's gonna be 3 numbers, and these numbers are in set A, okay? So set A has elements in it, okay? N number of elements. So it has like A1, A2, A3, AN. Okay, so it has a bunch of elements in here. So you're gonna pick 3 of them from here and place them in these spaces. So the ABC is a typical triplet, okay? But you don't want these to repeat. So how many choices of elements would you have for the first space? N. All right, and how many choices for the second space?
N-1.
Yeah.
N-2.
Right.
Okay.
So it's just the same permutation problems that we've been doing, but it's just it's basically yeah, it's a basic counting technique kind of thing, the permutation, but just kind of in the context, oh, you're making a triplet from a set. So instead of kind of going, you're rolling a dice and the numbers can't repeat, then it's just kind of just a different context.
Yeah, I think the keyword for me on that was the set of the N.
Right, okay. All right, let's get back to, all right, Lauren, okay. Exam 1 says it's available on Saturday, 9:25. Yeah, is that wrong?
So we're going to be taking our exams on Saturdays?
Yes, so the exams are not live, right? Basically, the exam opens at midnight, like 12 a.m. in the morning on Saturday, and it's going to be due 11:59 p.m. on Saturday. Once you open it, you have 2 hours to complete it. So basically, you open it, you're going to find a file in there. There's going to be approximately 10 problems. They were going to look similar to the ones on the problem sets. You need to do all work, take pictures, and submit it within that 2-hour period. If there's a problem for you doing on Saturday, just let me know, and I can either set it to be a day or two before or a day or two after. Okay. Is there a problem?
Yeah, I would rather take it the day before if possible, because I'm going to be out of town on Saturday.
Okay, so please send me an email so I don't forget, and then I can reset. Is it just for this this date or all your exams?
I think it's just for this one. I haven't looked ahead past this. I just couldn't remember if, or like, I didn't know if we were actually going to be taking it on Saturday or not.
Yeah, so just send me a quick email and then I can put that in today so I don't forget.
Okay, thank you.
All right, so then we're looking at basic counting techniques. Okay, so let me pull up your problem so we can look at it on the homework. Okay, so let's, this is, okay, okay, so there's two problems on there. Okay. All right.
I'm sure we did this one.
Chapter 2, basic counting techniques, Lauren. Okay. Number 11. Let's look at this one. All right, cool. So I think, Lauren, this is the first one you asked me about.
Yeah.
Question 11. Okay, so there's a one-to-one correspondence between the two element subsets of 1 to 20 and the positive integer solutions of x plus y plus z equals 21. Match each integer solution. Oh, okay. So you basically have to find what the rule is. So they don't tell you what the rule is, but you have to figure out how they relate to each other. Okay. So I see you answered it, but basically it looks like, right, if you have, let's see, so A matched with 511. Okay, so they all add up to 21. Okay. Okay, wait, I'm trying to figure out how this works. Let's see, F. Okay, so these add up to 20, and this one is by itself. Okay. These add up to, oh, okay. It's not, this is a bit weird. It's not like the one that I did. So this must be like a different kind of pattern. Okay, so let's look at this one. 15, C is 15 and 5. Okay, C is 15 and 5. So it's the sum and then the first term. This is 12 and 13. So the sum and the first term, but they're mixed up. Okay. So it's kind of, it's the combination of the sum in one place and the first term in the other. Okay. But some of them are twisted around, first term and the sum. Okay. So it doesn't seem to be consistent. Let's see. So let's look at all. So if I do, the sum is 15 and the first term is 5. The sum is 13 for this one. And the first term is 12. Okay, but these are switched. Oh, okay, they're just putting it. I don't think the order matters. It's just as long as you have one of them in the set, because it's a set with the squiggly brackets, the order doesn't matter. But the pattern for finding what is in the set is that you add, it's the sum of the first two and then the first term in the sum. Okay, so that's how it matches to what's in the right hand side. Okay, so yeah, for this first one, the sum is 10 and the first term is 1. So 10, 1 would be it. For this one, the sum is 11 and the first term is 5. So that would be that one. The sum is 20 and the first term is 1. So that would be that one. Okay.
Okay, thank you.
All right, cool. Let's look at the other homework, permutations, question 7. Okay. Yeah, that's, I think we were working on this last night in office hours. All right, so let me go to your stuff. Chapter 2, permutations. Lauren. All right, there you go. Number 7. This one?
Yeah, just part 2.
All right, so I see you got the right answer. So what was confusing about it?
I just am not confident in the method that I used to get the right answer. Like, I feel like I kind of just stumbled upon it.
Okay. All right, so we're looking in how many of the outcomes are there 2 dice with 1 value and 4 dice with a different value. Okay, so my thinking of this one, we have 1, 2, 3, 4, 5, 6. All right, so if we have two dice with 1 value and 4 dice with a different value. Okay, so for the 4, let's kind of just separate them. So this is 1 value and this is a different one. So for the 4 dice with 1 value, we have 6 choices. So let's say this is gonna be 1 through 6. So we have like 6 choices, but then here you're gonna have 1 choice, because once like a value was chosen for one of the 4, then you don't really have a choice of another value. It has to stick with the choice that was made. All right. And then with the 2 dice, because you don't want these to be the same value as the original one, then you have 5 choices for what that could be. And again, the second of the 2 dice, you don't have a choice because it has to be the same value. All right. So that would make it 6 times 5 is 30. Okay. All right, but now you need to count for how you can arrange it. Okay, so this kind of gives you 30. So it's like, how many ways could I arrange 1, 2, 3, 4, 5, 6 different things? Okay, so this is gonna be so like 6 factorial, but like 4 of them are identical and 2 of them are identical. So it's like arranging, I don't know how.
Because the way that I did it, like after this point, is that the first chunk, it has 3 different places where it could be relative to the 2 other die. So I multiplied 30 by 3. And then for the second chunk, there's 5 places that could be. So I multiplied it by 5, but I wasn't sure if there was like a different way to do that or if that was right.
Yeah, I mean, that goes right, but I'm trying to think where. So Okay, sorry. I'm trying to think of a good way of explaining where that comes from. All right, so yeah, within, yeah, how does that get multiplied by 15? So yeah, within here, yeah, these numbers are identical. It's kind of just how do we arrange them within each other? Okay, so like one way of explaining it, but again, we haven't done the combinations thing yet, so there must be a different way of explaining it, is that we want exactly 2 of them to be this one value. So out of the 6 places, you are choosing 2 of them to be this particular number. So this is 6 factorial over 4 factorial over 2 factorial. Let's see if that's the correct one. So 6, choose 2. That's 15. Okay. So yeah, that's where the 15 came from. But without combinations, like you said, so why is it 3 and 5? There's 2 identical things. And there's 4 identical things. Oh, right. Yeah, I think it's, yeah, like we're talking about the bushes and some of them are repeats, like when they repeat and things like that. So you have 6 places, so it's 6 factorial, because it's basically you can have like 6 different things in here. But then because like 2 of them are identical, you have to divide by 2 factorial, because when you switch these wherever they're located, then that's going to cut your number of different choices in half. So you divide by 2 factorial. And because these are 4 of these repeat, then you have to divide by 4 factorial, because that's how you can arrange these 4 identical things within each other. If they were different from each other, then they would be different numbers. But because they're identical, then they're gonna be copies of each other.
Okay, so the 6 factorial is like, when we multiply by that, it's us finding placements.
Yeah, so 6 factorial is basically in how many ways can you arrange 6 different objects next to each other. Okay, so that would be 720. I think that's what that is, right? But I don't have 6 different numbers. I have like 2 of them are identical. So you divide by 2 factorial to account for the repeats, because 2 of them are identical. And then 4 of the others are identical with each other. So you divide by 4 factorial, which is 24, to account that these are all repeats of each other. So when you do that, you get the 15.
Okay, that makes a lot more sense. Thank you.
Yes, sorry it took.
Oh, no, you're good. I was like kind of looking at it, and I realized that like another way that you could get like the value 15 was doing the 6 factorial divided by 4 factorial and 2 factorial. But yeah. I was like, I don't know why we would use that though. So.
Yeah, so yeah, it's kind of, yes, the arrangements of the thing. So yeah, the 6 and the 5 comes from how many choices you have for the first number, how many choices you have for the second, like picking 2 different ones. And then this mess, the 6 factorial over 2 over 4, comes from how do I arrange those 2 numbers that I have within each other, amongst each other, okay? And that's the 15 times. All right?
All right, thank you.
Sure, no problem. Yeah, there's more coming. Sorry. Yeah, I think my problem with these ones, like I can figure them out like after a bit, but it's just trying to explain them so they make sense. And I think it's easy to just like plug into a formula. I was like, here's the formula, plug it in. But I really like to for me to understand how things are working and to explain so you guys understand how they're working, and that's the difficult part.
Professor, could we do the number 1 for permutation homework?
All right, yeah, let me look at yours because yours might be different than Lauren's. So for permutations, number 1.
I'm having a hard time on the
Yeah.
question.
Oh, there it is. Okay. All right, so there we go. Okay, yeah, the first few problems are similar to this one, so that's good. Okay, so you have 13 math majors, 14 computer science majors, 8 education majors, and there's 35 of them in total, right? If you add them up. So you want president, vice president, treasurer. So for the first one, you just do 35 times 34 times 31, right? Is that what you did? 33. Sorry.
Yeah.
Why did I go down so much? Okay.
I did the permutation formula for it.
All right. So number 2, in how many of the election results do the president and vice presidents have different majors? Okay. So for this one, again, there's probably other ways to do it. But I was thinking, what if we do math and computer science? Okay, so you could have like math and computer science. And then this one could be any, including math and computer science. What if it's math and education? And this could be any. Or you could have computer science and education. And this could be any. All right. So let's see how many choices we have. So we have 13 for math and 14 for computer science. And then we use 2 out of the 35. So now there's 33 left here. Okay, so 13 times 14 times 33, we get 6,006. All right, math and education, 13 and 8, and then there's 33 left over. 13 times 8 times 33. So that's 3432. Computer science and education, 14 and 8 and 33 are left over. So 14 times 8 times 33, we get 3696. All right. Okay, so let's add these up. So 6,006 plus 3432 plus 3696. I got 13134. Okay, so we need double this because I did math and computer science, but because they're president and vice president, they're not interchangeable. So you could have the choice where the computer science person and the math person are interchanged. He could be president and she could be vice president. So you have to kind of basically do it again with the math and computer science, but roles are reversed, and here the same and here the same. So multiply everything by 2 and you're gonna get the 26268. All right, does that make sense?
Yeah, it makes sense, but is there a way for this to solve like mathematically? Like,
this is solving mathematically. This is what
I mean, is there like a formula that we can, because we're at permutation?
Yeah, this is a permutation formula, but it's not, this is a more complex case. So you are not only using the multiplication, like the permutation formula, like we learned, but you also have to break it up into cases. So you're using both multiplication and addition.
Oh, I see.
So you are using the formulas, but it's not as straightforward as number 1 because you have to consider cases. So no, it's not a, here's one formula that you plug in. you have, yeah, it's not plug and chug. And a lot of this class is not, here's the formula, go use it. I'm asking you to think, all right? So you got to think about these and construct a way to solve these problems, okay? Does that make sense?
Yes.
All right, cool, awesome.
Frustrating, but also fun.
Yeah, it is. This is the part of math that I like the most, including the frustration and the challenge, because that's what makes it fun.
For question 18 on the problem set, when we're given all the values for like 60 people owned an iPhone, is that like they only own an iPhone?
All right, let's see. Let's see how
They
it's.
own multiple phones.
They could, yeah.
We have 2 phones.
No. No, so 60 is, it could include other things. So it says there's 300 people in total, 60 own an iPhone, 75 own the BlackBerry, and 30 owned an Android. It says furthermore, 40 own both an iPhone and a BlackBerry. So out of the 60, some of them could also have a BlackBerry and some of them could also have an Android. So there will be people who have 3 phones.
So out of the 60,
yeah, 60.
the 40, like 40 of those 60 also own a BlackBerry?
Yes.
Wouldn't be a good Venn diagram problem?
Okay,
Yeah,
I was
so
just wondering because when I went to do problem A, I was like, oh, so like half of the people that they surveyed then didn't own a phone.
So yeah, you could have like A, B, C. So it's like A union, B union, C is gonna be the 300. So that's all the people. Oh, no, it's not, because some of them could have none. Yeah, some of them could be none. Okay. So A is 60 and B is 75 and C is 30. But then it says, if I do iPhone and BlackBerry, so A intersect B, that would be 40. iPhone and Android, so A intersect C is 12, and 8 on BlackBerry and Android, so B intersect C is 8, and 3 are all of them, so A intersect B intersect C is 8.
Yeah, the reason why I was confused is because if you look at where A intersects with the other, like the rest of them,
yeah,
like the numbers just didn't make sense to me. Like then there's only 9 people who only owned an iPhone, and then there's 125 people who didn't own a phone.
All right,
like
yeah.
that.
So yeah, the 60 includes, within that 60 set, it includes the people who also own BlackBerry and an Android and stuff like that. So yeah, so think of the Venn diagrams. All right, the 60 would be the entire circle. Oh, and you have like things in the overlap here. All right. Yeah, so yeah, go ahead. All right, so then out of the 60, if I subtract all these, 60 minus 37 minus 3 minus 9, only 11 of them just have an iPhone. The other of the 60 will also have another one. Mm-hmm. The what? Sorry.
They'll have 2 different phones.
The 11?
Yeah.
No, the 11 will just have the iPhone. Yeah. Because these are the people, these 3 have all 3 of them. These 37 have both an iPhone and a BlackBerry. And actually these 40 have an iPhone and a BlackBerry. And these 12 have an iPhone and a Android. Yeah, so if I do 60 minus all these people who already have other phones, then just 11 of them have just an iPhone. Out of 5. Yeah. And for Android, 30 minus 9 minus 3 minus 5 is 13. Good. So you can have the union either with the Venn diagram or the formula to figure out how many people have iPhones, Androids, and Blackberries.
This doesn't account for, we take all of those. Does that add up to 300 all of that?
No,
So
because some of them will not have any phone, any of those phones.
So we can take all that, add it up, and subtract that from 300 and find out how many people have that phone.
Exactly.
Okay. How much is that?
Yeah. Yeah, that's what I got to.
People don't have phones, and that would go outside of the circle.
Yeah, exactly. All the people in the universe.
So for like, if I wanted to say that 190 people don't own phones, could I do like cardinality of A union B union C complement?
Mm-hmm.
And that is.
Mm-hmm. Yeah.
Okay.
That's good.
That is a complement.
Yeah, yeah. Complement is really useful.